Today we're going to finish up the last part of the chapter on models of the atom, specifically writing electron configurations. Once we finish this particular portion of models of the atom, we'll go on to the next chapter, which is about the periodic table. All right, electron configurations involve periodic table. Now, so far in the periodic table, we've talked about basically just the elements and their symbols. We've talked about atomic number, and atomic mass. We talked a little bit about these numbers here, that there's 7 rows. And before we get into specifics of electron configuration, let's just review a little bit of how the periodic table relates to this idea of atomic structure. All right, you can see that down here we've got things we call the period. And period are these horizontal rows as we go back and forth on the periodic table. And you can see it's a set of 1, 2, 3, 4, 5, 6, or 7. Depending on where the element is on the periodic table, that number, called the principal quantum number, and we designate it with a lowercase cursive n, can equal the set of numbers 1, 2, 3, 4, 5, 6, or 7. So that means based on the position of the periodic table, each of these elements in its different row can have different energy levels, also called shells. Now, in the Bohr model, they show the nucleus, and then they show these nice tidy orbitals that go around and around the nucleus. Well, for the purposes of our discussion, this is a good model, but really and truly it's not this tidy. It's more like a golf ball inside of a softball, inside of a basketball, inside of a beach ball. That it's not always a circular orbital. It's more like a set of probability points where you might actually find an electron. All right, so this number n has to do with how many layers of electrons. So this would be n equals 1, n equals 2, n equals 3, and so on up to n equals 7. So the elements on the periodic table, hydrogen and helium, since they're in row 1, have a principal quantum number of 1. Lithium, beryllium, boron, carbon, all the way to neon, since they're in the second row with a principal quantum number of 2, they have 2 layers of electrons. The third row, principal quantum number 3, sodium and magnesium, all the way up to argon, have 3 shells, or energy levels, they might also be called. So that's why we can say that each of the electrons that we put in these, it resides in one of these 7 energy levels. All right, so based on that idea, we can take something simple. Say, for example, let's look at magnesium. Magnesium here on the periodic table. If we were going to draw a basic Bohr depiction of magnesium, magnesium is element number 12, and so that means it has 12 electrons and 12 protons. If you look at the structure of magnesium, here's the nucleus, and the nucleus would have 12 protons and some number of neutrons, we'll say 12, just for argument's sake. It could be more or less depending on the isotope. This is what we're worried about in the nucleus. So we have a plus 12 nucleus. So that 12 also means that we have to have 12 electrons. And we know that since magnesium is in the third row, that they're going to reside in 3 different energy levels. So if I was going to draw just the Bohr model, I'd say, all right, here's our first energy level, second energy level, third energy level. So n equals 1, n equals 2, n equals 3. And we're talking about magnesium again. Now the first energy level is full with 2 electrons, and that's the only one that's full. All of the other shells need 8. This is called the octet rule. An octet rule states that shells are full with the magic number of 8 electrons, and since that's the lowest energy state that the elements can have, that's the level that they strive to fill. They want to have 8 electrons. So back to magnesium. If you look at magnesium, it's got a total of 12 electrons that we have to distribute. In the first energy level is the only one that's full with 2. So we're going to put 2 of those electrons in the first energy level. So 12 minus 2 leaves 10 remaining. And remember, the max that can go in a particular energy level is 8. So we're going to put 8 in the second energy level. minus 8 leaves us 2 remaining. So that means in the outermost shell, also known as the valence shell, and the valence means it's the outermost energy level or share of electrons, there are only 2 electrons. And if we add them all up, we got 2 in the first shell, 8 more in the second shell makes 10, 2 more in this third shell is 12, so there's the magic number of magnesium. Well, if we wanted to write an electron configuration for magnesium, it's basically the shorthand version of a note-taking way of showing this in shorthand. And the shorthand version has the particular form of NXS. Whoops, let me write that over again. NXS. All right? So each of these means something. N is lowercase n, which is the principal quantum number. Remember, that's the set of numbers 1, 2, 3, 4, 5, 6, or 7 that corresponds to the row on the periodic table where that element resides. X has to do with the spin or area on the periodic table, and X can be S, P, D, or F. Those are 4 letters that designate the way a particular electron is spinning within the context of a particular energy level. So S, P, D, and F. They become more complex as you go from S, P, D, or F. If you look at a periodic table shadow box outline of where S, P, D, and F are, if you divide up the periodic table, that's section S, P, D, and this bottom section here is F. What do these mean? That means that as you put electrons in that section, and we'll talk about that in a minute when we finish electron configurations, but as you put electrons in that section, they spin in different ways. S electrons are sort of the fried pancake, a fried egg sort of thing, where you've got the nucleus in the middle, like the Bohr model, and it spins in a circular direction. They can spin in one direction. They can also spin in the opposite direction. P spinning electrons have kind of a dumbbell shape to them. D spinning electrons looks more like a tetrahedron with 4, and F spinning electrons are so complex I couldn't even draw them. So this has less energy it takes to go into an S electron. Takes more energy to go into an F electron because of the complexity of their spin. Well, what does that mean if we were thinking about the Bohr model, this whole idea of spins? Well, if we look back at our magnesium atom, we see that magnesium has 2 electrons in its first shell, and the first 2 are always S spinning electrons. In magnesium's second shell, we have 8. 2 of those are S spinning, and 6 of those are D spinning. What that means is if we take this electron and that electron in the second shell and say they are S spinning electrons, that one is going to be spinning in a circular path in that direction and the other one is going to be spinning in a circular path in the opposite direction. So this S spinning electron will spin circularly this way, this S spinning electron will spin circularly this way. Only 2 of the 8 in every shell spin in this S direction. The other 6 spin in the P spinning direction. And if in my mind, how I equate this is I say, all right, the P spinning electrons go out to the same energy level, right? They're going out to n equals 2, the second shell. It's just that the way they spin is different. If it was an S spinning electron, it would spin in a circular orbit around the nucleus. That's an S spinning electron. If it's a P spinning electron, it spins in this sort of figure 8. But keep it in mind that it only goes that distance from the nucleus, and that's why it's still considered a second level electron. All right, so back to electron configurations. NXS, N is the principal quantum number. X has to do with S, P, D, or F, so X can be only one of those 4 values. And S has to do with the number of electrons in that sublevel. All right, so there's the basic definition. It helps when you're doing this electron configuration thing to actually go in and do some of them, and then you'll see where the explanations come in. All right, so let's say we'll start with something super simple like hydrogen. And remember, we've got our S, P, D, and F spinning electrons, which correspond roughly to this as s spinning, this area as p spinning, this middle area are d spinning, and this bottom block here are the f spinning electrons. All right, so if we're going to do electron configuration, we'll do some simple ones first. Let's start with hydrogen, keeping in mind that our general form is NXS. Hydrogen, I'm going to put the symbol and put a semicolon. Hydrogen is in the first row, so you put the number 1 for the principal quantum number. X is the way that it's spinning. It's the electron we're talking about, the single electron that hydrogen has, is in the s block, so we have to put an s. And there's only 1 electron there. Easy peasy. Helium, almost the same. Actually, we're going to skip helium because it's an odd one. Let's go to lithium. Lithium, you've got to go through all the other electrons before you get to lithium. So if we were going to do the Bohr model of lithium, we would say lithium is here. It's got 3 positives in the nucleus. It's in the second row. So it has 2 layers of electrons. The first layer is full with 2. The second layer only has 1. So that would be what the Bohr model looked like. If we want to do it in electron configuration terms, we say, all right, we have to show the first layer of electrons. So we have to go through helium and hydrogen. So we say 1s2. That shows those 2 electrons in the first energy level, and they are s spinning electrons. One is spinning in one direction and one is spinning in the other. In the second energy level, since lithium has a total of 3 electrons, 2 we've used in that first shell, that third electron goes in the second shell. So now we are in the second principal quantum number. We're still talking about an s spinning electron, and there's only 1 of them there. All right, so let's go something a little bit more complex, like our magnesium. And remember, this was our Bohr model of magnesium, pretty messy. If we go to magnesium and we say, all right, let's just write the electron configuration for magnesium, we've got to go through everything before we get to magnesium. So hydrogen and helium is 1s2. Then we go lithium and beryllium, which is 2s2, so it's the second principal quantum number of the second row. We have 2 s spinning electrons, 1, 2, s2. Now we go over to the periodic table. Now we're in the p block, right? So now we're still in the second row, but now we're talking about p spinning electrons, and there are 1, 2, 3, 4, 5, 6 of them. So now this shows me I've gone through 1s2, 2s2, 2p6. I still have to get to magnesium, so now magnesium is in the third row. It has s spinning electrons, and it's in the second position. So there's the electron configuration for magnesium, and magnesium's atomic number is 12. So if you add up the exponents on your notation, they should equal that number, because that's the total number of electrons that you have in that atom. So 2 and 2 is 4, 6 more is 10, 2 more is 12. All right, let's try something a little bit more complex. Let's try, I'm going to throw a caveat in here for you. The d block of electrons lags 1 behind in principal quantum number. So d block, make a little note to yourself, lags 1 behind in principal quantum number, which we abbreviate with n. So that means when you're looking at the periodic table and you look at something like vanadium, you'd say, okay, that's 1, 2, 3, 4. Those are 4s electrons, but since the d block lags 1 behind in principal quantum number, that's not 4d electrons, those are 3d electrons. So let me show you what I'm talking about. Let's do iron. All right, the electron configuration for iron. So if we look at iron, iron is here, element number 26. So it's got to have a total of 26 electrons. So we want to put them all in. So we have to start at the very beginning. So we say 1s2, 2s2, 2p6, because I have to go through all 6 of those. Now I'm down to the third row. So now I write 3s2, 1, 2. Now I go across. It's just like reading a book. First row, second row, third row, and so on. So now 3s2 I've written. I'm still in the third row, but now I'm in the p spinning electrons, and there's 1, 2, 3, 4, 5, 6 of them. Now I go back to the s block because I got to get to iron, which is here, so I have to go through some s spinning electrons. That's the fourth energy level. There are s electrons there, and there are 2 of them. Now I get into the D block, which in this case now lags one behind in principal quantum number. So instead of 4D, it's 3D, and iron is in position 1, 2, 3, 4, 5, 6. Okay. Let's do one more with some D block elements in it to make sure that we know what we're doing here. Let's try silver. Silver's a good one to use. All right, Ag. So if we go through, there's silver. We have to go through the 1s electrons, the 2s electrons, the 2p electrons, the 3s electrons, the 3p electrons, the 4s electrons. Now we're back in the D block, so it's 3D, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now that we're in the P block, we have to go back to the real level, which is, I'm going to move this down here a little bit, 4P, and we have to go through the whole block, 1, 2, 3, 4, 5, 6. Now we're down in the fifth row, so that's 5S, and there are two of them. And we get to silver. Now you would think that's a 5D, but remember, D lags one behind in principal quantum number. So it's actually 4D, and it goes 1, 2, 3, 4, 5, 6, 7, 8, 9 is where silver is. All right? There is a shorthand way to abbreviate these electron configurations. Let's look at the shorthand way. Shorthand uses what we call the core electrons. All right, core electrons means the element that directly precedes whatever element you're writing the electron configuration for, that's one of the noble gases, that's considered its core electron. So if we look at iron, iron is here on the periodic table. The noble gas directly preceding iron is argon. So we can say iron is the same as argon, except with 4s2 and 3d electrons added to it. So if we want to abbreviate iron's electron configuration, we can write Fe, and we simply put argon in square brackets, and that's how we designate the core electrons, right? And that takes off everything here. So those are the core electrons. So now all you have to write is everything past argon. So there's argon, 4s2, 3d, 1, 2, 3, 4, 5, 6. So 4s2, 3d, 6. Let's do the same thing for silver. Let's write the shorthand version for silver. Here's silver. The noble gas directly preceding silver is krypton. So in order to write the shorthand for silver, we would write Ag is just like krypton's core electrons, and then we have to write everything after krypton. So that is 5s2, 4d9. So there's the shorthand version for silver. All right? Okay, one last little nuggets of information with electron configurations. You need to know the valence electrons. Well, let's look at these. Remember, valence electrons are the electrons on the outer shell. These are the valence electrons. I'll use a different color. And let's look and see what the valence electrons are. All right. Valence electrons are always the outer shell. Something like magnesium, it's pretty easy. Valence electrons are simply the 3s2 electrons. It gets a little bit more difficult when you get these ones in the middle because those fill in an odd way. So what you have to do for iron, if we're using the full-on iron electron configuration, the valence electrons are only those electrons right there. So you look at the highest principal quantum number. So Fe only has valence electrons in the 4s2 configuration. Also, we could do the same thing for silver. If we look at the full-on electron configuration for silver, the highest principal quantum number here is 5. So the valence electrons for silver are 5s2 electrons. Finally, we need to know how to write electron configuration for ions. Let's do a positive ion first. Let's say iron. When iron loses an electron, it becomes an iron plus 2 ion, plus those 2 electrons are lost somewhere. So if we were going to do the normal electron configuration for iron, we would say it is Fe is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, and iron is 1, 2, 3, 4, 5, 6, position 6. All right, so that's normal iron. Fe with a plus 2 charge has lost 2 electrons, but they must come from the valence shell. So since that's the valence shell, those electrons would just go bye-bye, and the electron configuration for iron then would be this. So there's the electron configuration for iron plus 2. Let's try one like chlorine. Chlorine, on the other hand, gains an electron to become a chloride ion, so we'll need to depict that. Normal chlorine looks like this. Here's chlorine right here. So if we write the electron configuration for normal chlorine is 1s2, 2s2, 2p6, 3s2, 3p, 1, 2, 3, 4, 5. So 3p5. When electrons are added, just like when they're taken away, they're added to the valence shell. So to make this the electron configuration for Cl-, we would simply add the last electron in the space that it could go, in this case, p electrons. So s electrons, max electrons, they can have 2 electrons max. P spinning electrons, they can have a maximum of 1, 2, 3, 4, 5, 6 electrons. D spinning electrons, you look at the spots for D, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 electrons max in a D, and F, the really complex ones, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. It should be 14, I think I counted wrong. All right, so there's 14 electrons max in F spinning electrons. All right, that's the last part of models of the atom. I'm going to stop the recording now.